Anyway, all you have to do is ask a question and you get a candy. All right, so you've got it turned on? Okay. So I'm going to be talking about Fourier and Laplace transforms, and because I was ill and missed class on Tuesday, because they didn't find anybody to sub for me, and because now I'm forced to give a midterm, which is going to use up a class day, I'm going to go through this material the way I did last Thursday when I was ill and didn't realize how ill I was. I'm going to skip all the examples. Now, if you want to hear about the examples, come to the problem session on Wednesday, 5 o'clock, room 5, whether or not you're registered for that, and you can learn some of those examples. The examples are important for you to know about, but I'm going to skip them in today's lecture. Now basically with Fourier series like this, you're automatically representing a function that's periodic with period L. And so the question is, how do you get beyond that to represent an arbitrary function? And once again, Monsieur Fourier comes to our rescue. And the trick is just to look at these Fourier series and inverse Fourier series expressions and let the integral go to infinity, let L go to infinity, and just basically it's a change of variables, or it's the way I did it in my book, it's a sequence of changes of variables. By the way, the book's available in the bookstore physically, and as well as on Amazon. And by the way, the book is half the price of the usual book. The usual book is like $150. My book is $85 or something, and or $80 at Amazon. Okay, so the first step is to use what's called the nearest integer function, and that just converts a real variable y into an integer, and so that allows us to turn f sub n into a function of a variable which we'll call y. And so when you do that, the expression for the Fourier series, then it's a sum of integrals of the Fourier transform. We can write it as an integral of this Fourier transform function in which the phase is exactly I 2 pi n x, because n is the variable that's closest to y. Anyway, the integer closest to y. Sorry. So we can then write the Fourier series as an integral from minus infinity to plus infinity, and we've just got this greatest integer function here. Well, that's almost writing it as a Fourier transform. And the next thing is to realize that if L is huge, in fact, the limit L going to infinity, the difference between y equal to y and y equal to the nearest integer to y is small when divided by capital L. So we can just replace that variable just by y. So we can drop the greatest integer. By the way, this greatest integer is a standard function. It's just one that's not talked about much in physics classes. So now we've got the function written as a Fourier transform. We're essentially done, and all we need to do is make a couple of changes of variables so that this doesn't look so clumsy. So we let y equal to lk over 2 pi, which means k is 2 pi y over L, And then this thing turns into that, and now it looks even worse. But if we define the Fourier transform as this thing, namely square root of L over 2 pi times f hat of Lk over 2 pi, we arrive at the Fourier transform formula. And then to invert things, we go back to what f tilde is. Well, f tilde is this thing, and this thing, in turn, was defined as well, in terms of the greatest integer function. Anyway, what happens is f tilde is then this, which is this integral from minus L over 2 to L over 2. And now, canceling things out, we get this. And so then we're basically done. We have that the Fourier transform is an integral from minus L over 2 to L over 2. We just take the limit. L goes to infinity. And now we have the Fourier transform is the integral of the function e to the minus ikx over square root of 2 pi. And so we've arrived at these Fourier transform relations. The function is an integral e to the ikx over root 2 pi over the whole real line. And the Fourier transform is the same integral of the function with the opposite phase, and again divided by root 2 pi. And so we say for f tilde of k is the Fourier transform of f of x, and f of x is the inverse Fourier transform of Fourier tilde of k. And of course, as with the case of Fourier transforms, which you call, well, no, actually, in this case, they really are symmetrical, whereas with the Fourier series, one is a function defined as an at integers, and the other is an integral, and so forth. Here, these two things are entirely symmetrical, and it really doesn't matter whether you put a plus ikx here and a minus there, or a minus here and a plus there, and whether you put the 2 pi's this way or you put them that way. It doesn't matter, you just have to use the same convention in the same problem. And my advice to graduate students is to pick the convention you like and stick with it, don't mess with other conventions. But realize how to get from one to the other, because if you're following in some book on electrodynamics or mechanics or quantum mechanics, you're going to see different conventions used, so you need to be able to switch from this one to the one I just wrote as the symmetrical one. Any questions? By the way, you'll learn more if you sit in row 1 than if you sit in the middle. Although in this classroom, when I lecture on the board and cover all the blackboards, it doesn't matter where you sit. But when I'm lecturing this way, you're better off being in the front. Anyhow, sometimes, especially in physics problems, you need to switch between Fourier series and Fourier transforms. And so you need to know how to do that. And it's basically a change of variables, and you just have to keep things straight. And so what you do is you write your function as a Fourier series, and then you write it as a Fourier transform, and you then change this variable to case of n, and then you remember the definition of f tilde in terms of the Fourier series variable. And so then you realize that your Fourier series representation looks like this, and can be rewritten in terms of the Fourier transform variable evaluated at discrete momenta, namely case of n. And going the other way, if you have the Fourier series variables, you can write the function as the integral of its Fourier transform, and as the Fourier transform, you use the Fourier series variable evaluated this way, and then you stick in the capital L and the square root of L and so forth. Okay, any questions? You really should ask questions, even if you don't want candy. In fact, one reason to ask questions, even if you know the answer, is to help out your classmates who have no idea what the answer to the question you ask is. Another reason to ask questions is that you then become noticed by the professor. And if you ask questions in all your classes, you'll be one of the famous students. You'll no longer be meaningless, you will no longer be one of a bunch of graduate students the faculty can't remember. You'll be memorable, and you'll be better off. Anyhow, I said I'm going to have to skip the examples. Let me just tell you what the Fourier transform of Gaussian is. Well, it's this integral, and the answer is this. So if your original Gaussian is e to the minus m squared x squared, your Fourier transform Gaussian apart from an overall factor is another Gaussian, but the m doesn't appear here. It divides the k squared, multiplies x squared, divides k squared. What this means is that the way a function behaves, if a function behaves one way in position space, it looks the opposite way in momentum space. So in other words, if it's large at large momenta and small at small momenta, then in position space, it's large at small positions and small at large positions. And that's very important from the point of view of physics. In physical problems, that's very important. So that's the rest of this example. We're going to skip that. Now, what if a function is a real function? Well, if it's a real function, you take the complex conjugate of the Fourier transform, you flip the phase, but nothing happens to the function because it's real. And so then this is the formula for the Fourier transform at the negative value of k, at minus k. So if the function is real, then the Fourier transform at minus k is the complex conjugate of the Fourier transform at k. That implies these relations, which are that you could write the function as a double integral of a cosine, or in one way or as a double cosine and a double sine, depending on whether it's real and even or real and odd. I'm going to skip the examples. Any questions? The next topic is really important in physics because delta functions are used all the time in electrodynamics and quantum mechanics in physics. In fact, when you go from momentum space to position space and back again, you find yourself continuously using Fourier transforms and delta functions. That's the reason, by the way, why I put these chapters early in the book, as opposed to after complex variables and differential equations. I put them early because you've got to know about Fourier series, Fourier transforms, and linear algebra if you're going to do quantum mechanics. And for electrodynamics, you have to know about the Fourier transforms. Linear algebra is less crucial, typically. Okay, so let's use our Fourier transform formulas and see what happens. And what happens is a magic that was once again brought to us by Paul Adrian Maurice Dirac, who was quite a remarkable man. He was famous, by the way, for using as few words as possible, and sometimes for not even answering questions. In fact, a student once at Cambridge University asked him a question, and there was no reply. And the student complained. He said, I asked you a question, you didn't answer. Dirac said, what you answered, what you said wasn't a question. I once asked Dirac a question. He did not reply at all. I said, what do you think about Mandelstam's work on supersymmetric n equals 4, quantum field theory being finite? No answer. Anyway, of course, at that time, he was probably 95 years of age. He died a couple of years later. Anyway, so if we write our function as a Fourier transform, and then we write the Fourier transform as an integral of the function, and then rewrite that double integral this way, and then compare that with the expression for the function in terms of itself via a Dirac delta function, we realize that this thing in parentheses is a representation of Dirac's delta function. And this, in fact, is the representation that is the workhorse, one of the workhorses of mathematics and quantum mechanics. So this thing is your friend, and you must become really familiar with it. It should be kind of an intellectual pillow that you sleep on. And let's look at it, not in this limit from minus infinity to plus infinity, but let's do the integral numerically from minus a million to a million, and let's plot the result. What do we get? Well, I used MATLAB to do that, and what I found was this. And notice the two scales here. We're going from minus 10 to the minus 3 to 10 to the minus 3 on the x-axis, and we're going from minus 1 to 3.5 times 10 to the 5th on the y-axis. And even with this crazy stretching of axes by 10 to the 8th, the delta function, which is not the exact delta function, but this approximate representation, is this incredible spike. So this is why the delta function formula works. As you see, if you truncate it to something reasonable, you still get an amazingly accurate representation of the delta function. And so that should convince you that this function, this representation is actually true. You do it on MATLAB and you see, MATLAB tells you that's what it is, numerically. It is, by the way, extremely useful in general in theoretical physics to combine, and engineering generally, to combine concepts with numerical examples. Because in order to work out for yourself a numerical example, that process ties your thoughts down firmly to the reality of what you're trying to think about, in a way that if you take too much the poet's approach to physics, you can lose sight of. Oh fuck! It says low battery on this. All right, let's see. I've got this thing attached. There's no green light. Oh, nobody turned the damn thing on. Let's see if that makes it work. No. It's still not on. Well, this is pretty ridiculous. We have a socket here that has no electricity. Let me phone good old Tom. Is there a socket over there? All right, let's see if we can put this in the socket over there. I can, but thank you. Although I really, in my condition, I should have let you do it. No, it's still dark. Now it's on. Okay, so the lecture's saved. Well, modulo my mistakes. So now that we've learned a little more about the delta function, let's look at what the inner product of two functions is. And of course, it's an integral of the complex conjugate of one times the other from minus infinity to plus infinity. And we can write this in Dirac's notation this way. The mathematicians would like to write it this way, but I think we're just as well off staying with Dirac. And notice how this bears out what I said in chapter 1, namely that you should feel perfectly free to put differential or other kinds of mathematical operators in front of the F or in front of the G, because on the right-hand side that would just mean that in the integral they occur here or there with a complex conjugate, with complex conjugation. And I think it's a bit of a shame that we religiously almost just write psi here and x there when it's so much more general what Dirac gave us. So let's write this in a product formula in terms of the Fourier transforms of the two functions. And so it's an integral over x of one Fourier transform times another. We multiply them together, and we see we have here an integral of x, e to the I k prime minus k, but that's just our delta function formula with, I guess, x and k interchanged. So this is a delta function of k prime minus k, which of course reduces a double integral, which you'd hate to do, into something that's just a single integral, which is a lot easier. And so now, putting those together, what we see is that this inner product is the same thing as the inner product of the Fourier transforms. And so we can say that Fg is F tilde G tilde, or in Dirac's notation it's Fg is F tilde G tilde. And what this says is that the Fourier transform is a unitary transformation. It preserves inner products. The inner product of momentum space is the same as the inner product in position space. And this is called Parseval's relation. And if you set F equal to G, you have that the inner product of a state with itself, which might be an integral of the function, the absolute value squared of the function over all arguments, is the same thing as the integral of its Fourier transform, the absolute value of its Fourier transform. And in fact, the situation is actually somewhat nicer mathematically. And this is one of the reasons why mathematicians like Lebesgue integration. Because if you have the Lebesgue definition of square integrable functions, then the Fourier transform maps the space of Lebesgue's square integrable functions onto itself in a one-to-one fashion. And so that's exactly what you want in a mathematical relation. That's why the Fourier transform is so important in mathematics and especially in physics. It also tells you that the Dirac's delta function is a natural represent as an integral. Is the integral that I just was displaying is a natural representation of the delta function for continuous square integrable functions. Let's now go to something that's used without proof a million times in quantum and in electrodynamics, namely, what's the integral of a function times the delta function of another function. And the answer is quite simple, and let me just derive the answer for you in a pretty simple way. So first, let's assume the simple case, namely that the function g vanishes only at a single point x0, and consequently, and at that point, the derivative of the function is not 0. So we've got a unique point on the real axis where the delta function hits a 0, and of course that's where the spike is, because delta of 0 is infinite, delta of x not equal to 0 is 0. And so this integral is only sensitive to the value of the function f at that point x0, so we can pull out f of x0. So then this integral j is just this. But now we know the delta function is obviously positive. I graphed it for you and showed you it was positive. And so we can first of all approximate, of course I'm assuming that this function g is differentiable. So we can write it near x equal to x0 as g prime of x0 times x minus x0. We write it this way. And then we can multiply and divide by the absolute value of g prime of x0. And now this thing here is how g is increasing. This is essentially dg. In other words, g prime dx is dg. And this thing here is g minus g0 dg. And so this just integrates to 1. And so the whole integral j is just f of x0 over the absolute value of g prime of x0. It's the absolute value because the delta function is positive. And so the sign of j is the sign of f at x0. And it doesn't care anything about g. It cares only that g should vanish somewhere, and that's the value of f of x at which it evaluates the function f. So if f has if g has a single 0 at x0, then this integral is this. And equivalently, the delta function is delta of g of x is delta of x minus x0 divided by the absolute value of g prime of x0. And then obviously you can just repeat, yes?
Could you please repeat how you got
Louder.
Yeah.
Hi. I'm teaching. We can talk later if you want. Anyway, why don't you, I'm hard of hearing, why don't you scream?
Yeah. Could you repeat how you got to 4.45?
How I got to 4.45?
Yeah, from the one before that.
Right. All right, let me say, first of all, I agree with you. I think that I haven't made that crystal clear. So let's see. It's clear that we have to write it this way. That we can write it this way. It's also clear that this thing here is just g minus g0. So we can replace this part by that. And then this thing here is just dg, but it's a funny kind of dg. It's dg that's only positive. But the only effect of that being dg that's only positive is that the sign of this whole thing is positive. But the sign to the right-hand side has to be positive because it's just the integral of a delta function and that's always non-negative. So that's how I go from there to there. And certainly the integral of delta g minus g0 dg, that's just 1, because that just has a spike when g hits g0. When g is not g0, it's 0. It hits the spike and you just get 1. So this integral is clearly 1. So this part. All right, I hope that's okay. You know, I have an office down there. I'm in the office almost every afternoon when I'm not in the hospital. Frankly, I think Tuesday, I think, is the first class I've missed since 1981. Okay, so these things follow. This is an example, as I say. I'm happy to do those examples in the problem session on Wednesday. And in fact, if you want to if you want to learn more about those problems, a particular example, come to the problem session, ask me to do a particular example. I'll be happy to do it. Let's go back to the example of a Dirac comb. That I talked about, that we learned about in the Fourier series example, and that I illustrated in the book with a MATLAB example, numerical example. By the way, full disclosure, 10 years ago, I don't think I had ever heard about the Dirac comb. It's not something we talk about that much in physics departments. And in fact, in math departments, still less. I learned about it from a colleague of mine who was particularly interested in Dirac's work and told me about it. If you want a funny story, I'll tell you a funny story about a friend of his, but maybe I shouldn't do that or apply to the universe over the internet. Anyway, they're all very good physicists. So here's the Dirac comb from the point of view of Fourier series. If we write the, if we multiply both sides by an arbitrary function, when I say arbitrary, I mean suitably well behaved, we get this expression here. And the delta function in the Dirac comb will just turn this thing into a sum. And the integral here, well, this integral is this thing is a sum. This is an integral of the Fourier transform evaluated at integral values. So this is a weird sort of formula where on the left-hand side we have a sum, but it's a sum of the Fourier transform evaluated at integral points. And on the right, it's the function evaluated at integral points. But one is the Fourier transform, the other is the function. And if we look at this in the stretched form, then it's this way. Frankly, I don't think the stretched form helps that much. So I would tend to say focus on this. And you might say, boy, this can never be useful. In fact, this is actually a workhorse in certain areas of electrodynamics and chemical physics. Because remember when I said to you that the Fourier transform and the function behave differently. One might be big at large x. If one is big at large x, the other is big at small k, and vice versa. What that means is that one of these series converges immediately, and the other one takes forever. For example, if this one is big at large if the function is big at large x, this takes forever to converge because this thing is always big. On the other hand, this one is only big at small k, so this thing converges in a few terms. And so people who do electrodynamics and other things, a guy named Ewald invented a way of applying this. This is a Gaussian example of this formula, or rather, more simply, of this formula. And this is called Ewald's summation, and it makes things converge much more quickly. So now there's this business of derivatives and integrals of Fourier transforms. One of the lovely things about Fourier transforms is they're so easy to differentiate and integrate. And it's just trivial. You differentiate by x over here, and over here, all you have to do is differentiate an exponential. Well, you know, differentiate exponential, that just pulls down an ik. You do it twice, you get minus k squared. You do it n times, you get ik to the n. Of course, here I'm always assuming that the function is suitably well behaved, that there's no issue with differentiating inside the integral sign. You can also do indefinite integrals of Fourier transforms. You indefinitely integrate e to the ikx, and you get e to the ikx over ik. You do it n times, you get that. And whether the derivative of the integral converges better or worse than the function depends again on how the Fourier transform behaves at small and large k. Okay, here are some examples of momentum and momentum space. These examples lie at the basis of quantum mechanics. I'll be happy to do them in detail in the problem session if you want, but we're going to skip them now. One of them is the uncertainty principle. One of them is the mean value, the definition of the variance. Those are important. In fact, they're key problems in the theory, the key concepts in the theory of probability. But you can't do everything. There's Heisenberg's uncertainty principle derived for you as a consequence of the Fourier transform. Here is a definition of the characteristic function, which is a key concept in probability theory. When I was an undergraduate, I never took a course in probability theory. I became a graduate student without knowing about, ever hearing about characteristic functions. Turned out they're very important in probability theory, and anything that's really important in probability theory is important in physics, because of course physics is really all about probabilities, even classical physics. You're not, you know, as the people in who were the spokesman of fashion, the chaos fashion, taught us we have to approximate things in physics, and we often don't know what's exact. So what if you have a function of two variables? How do you make the Fourier transform? Well, obviously you just do this. You just do a double Fourier transform. And if you then invert the double Fourier transform, you get the function back, and so the function is then written as the Fourier transform of the inverse Fourier transform. If you are doing it in n variables, then this is the way it looks. The function looks like this, and the Fourier transform looks like that. And if you do it symmetrically, you have to divide by 2 pi to the n over 2, 1 root 2 pi for each variable. And if you want to go between Fourier series and Fourier transforms, you go back to the relations that I derived, and full disclosure, when When I was a graduate student, I regarded changing variables as too trivial for words, and so I never bothered to go through the steps in super care. And as a result, when I needed to figure out what the relationship was, because I was doing a problem where I knew the Fourier series, but I didn't know the Fourier transform or vice versa, I was stuck, and I had to figure things out from first principles and look them up in the book. Well, I derived for you in the early sections of this chapter the relation between the Fourier series variable and the Fourier transform variable. If you generalize that to n dimensions, then the function can be written as a Fourier series in terms of the Fourier transform variables evaluated this way. So you do the Fourier series and you divide by this and you multiply by that, and the kj's have discrete values, and that gives you the function represented as a Fourier series in terms of the Fourier transform, if you know the Fourier transform. And in particular, for 3 dimensions, you have this relation, which you've no doubt seen 10 or 20 times as an undergraduate. The function, as a function of 3 vector x, is 2 pi cubed over the volume, the sum over the Fourier transform variables, the Fourier transform evaluated momentum space at these discrete lattice points in momentum space, and you divide by L cubed and so forth. An example from quantum field theory is the Feynman propagator. We're going to skip that again. It's this, by the way, is the Heaviside function invented by Mr. Heaviside, which I think is really a remarkable coincidence of the guy's name with the mathematics. So any questions? Okay, convolutions. Convolutions, frankly, full disclosure, is something I didn't learn about very much as an undergraduate. I suppose I must have had a passing acquaintance, but I never really noticed them, and I may not have even have heard about them in a course or a book. But I did learn about them as a graduate student. And the definition of a convolution is this. I mean, actually, of course, as an undergraduate, in physics, I saw many examples of the convolution. I just didn't hear it called a convolution. So the convolution in one variable is defined this way. It's a funny sort of integral. F of x minus y, g of y integrated over y. Now it's actually symmetric, so f star g of x is the same as g star x of y, and the way you see that is you write f star g of x, you let z equal x minus y, you screw around changing variables, and you get this, but that's just the definition of g star f of x. And then, as I said, to me convolutions look weird at first, but in fact I then realized that those were the things that you see a million times, especially in electrodynamics, and also quantum mechanics, namely that an effect is given by a source integrated by something that transmits the cause to the effect. So a cause gets transmitted to an effect by means of something that depends upon the relative displacement between the location of the cause and the location of the effect. And this thing G is called a Green's function in general. And it's named after George Green, who was an English physicist or mathematician. One Nobel laureate who was one of I was fortunate to have him teach me quantum mechanics, Julian Schwinger, was particularly liked the work of George Green. In fact, I think he once made a side trip to Green's birthplace in England when he was touring England at some time. Anyway, let me give you some, this is a convolution, obviously, and let me just give you an example. And as I said, in the problem session, I'll be happy to do it for you. And it is that the Green's function in electrodynamics looks like this. And in particular, then, the electrostatic potential at a point is the charge density divided by the electric constant and x minus x prime integrated. This is a particular Green's function. And the magnetic and static potential, a current, this is static magnetostatics. It's again a convolution integral, and you must have seen things like this as an undergraduate. So much for convolutions. What about Fourier transforms? Well, again, as you can tell, I'm enamored of the Fourier transform. There are just so many nice things about the Fourier transform. And one of the nice things is, if you take the Fourier transform of a convolution, bingo, it's the product of the Fourier transform. So, what could be better than that? And so you take this Fourier transform, you just write it as, you just take the Fourier transform of the convolution, what is it? Well, you rewrite the convolution this way, and now you write f and g as their Fourier transforms, and you have this thing that's a quartic integral, and of course without Dirac's delta function we'd be totally baffled as to what that could possibly mean, but with his delta function it collapses into this and then that and then this, and bingo, it's the result. The Fourier transform of a convolution is the product of the Fourier transforms. And so that's just a wonderful result. So, as I said, as a graduate student, two of your best friends are the Dirac delta function and the Fourier transform. The Fourier transform made simple by the use of his delta function. So, is there a question? By the way, I wish the three of you would send me an email as to whether you prefer me to lecture this way through the computer, or whether you prefer me to write on the blackboard and, cover all, 10 blackboards in this room with chalk. Is that better for you as a learning experience, or is it better for me to go through things this way? I don't know. I'm not on the other side of it. Do you have any opinion right now? All right, well, think about it. You've seen me lecture this way twice. And, of course, the last time I didn't realize it, but I was running out of blood. And then when I was given a transfusion, a few days later, because I was too weak to do anything, the blood they gave me was bad blood, and that nearly killed me. And then they saved me at the UNM hospital. Okay, Fourier transforms and Green's function. Once again, as I say, these Fourier transforms, these Green's function, these convolutions, they're all your friends. So, what is a Green's function? In general, a Green's function is something that solves your problem. For example, suppose you are you have some differential operator P, and you want to solve this equation. You might say, well, why do you want to solve this equation? Well, if you solve this equation, you immediately figure out how to get solutions of the differential equation p times a function is anything at all. So you've solved all differential equations involving p if you can figure out what g is. And to figure out what g is, you just write p as a, this again is for the simple case where p is, say, something like a polynomial or a simple function of derivatives, and not also a function of the variable x. If it is that, then you've got an issue with mathematics, and it's not trivial. But if it's just a function of the derivatives with constant coefficients, then it's easy to find the Green's function. What you do is you just write down this equation, and then you write g as a Fourier transform, and you write g as a Fourier transform. So g is some Fourier transform of its Fourier transform, and p is a polynomial in derivatives. And when that p hits e to the ikx, it turns p into a polynomial of ik. And you want that to be the n-dimensional delta function, which is this. But then this is just an algebraic equation, because that's just pg is 1 over 2 pi to the n. So that means g is just 1 over 2 pi to the n p of ik. So you're done. The Green's function for the polynomial differential operator p is just effectively an integral, a kind of Fourier transform of 1 over p evaluated at ik. And this is what leads you to Green's functions of Yukawa and other ones that, again, are used all the time in physics, electrodynamics, quantum mechanics, quantum field theory, so on and so forth. No doubt string theory and so on. Okay, questions? Once again, especially if you think I'm going too fast, come to the problem session, ask questions, you can do the examples, or you can ask questions about homework. That's also legitimate. So let's now go to Laplace transforms. And as I've mentioned to you, Fourier transforms are basically good for anything that's square integrable. Technically, Lebesgue square integrable, but in physics departments we don't distinguish typically. Square integral. And but of course there are functions that aren't square integrable. The remarkable thing about the Laplace transform is if you write e to the minus st instead of e to the ist, you get better convergence, and you can have things that grow at large t, and you still are able to define the Laplace transform. For example, the function f equal to 1. Well, its Laplace transform is just e to the minus st. That's just 1 over s. So no problem. That's even square integrable over for positive values of s. And other examples are f of t might be an increasing exponential. The Laplace transform is perfectly well defined. In fact, it's well defined for arbitrary complex s and k, and it's just infinite when s equals k. And if you combine this relation and apply them to these things on the left, you can easily derive these relations for what the Laplace transform of Cauchy and Sinh, which are exponentially divergent. They still have finite Laplace transforms. And cos and sine are also oscillating, but they have Laplace transforms. This is a biophysics example. By the way, biophysics is a very good field to get into. It's a field in which you're essentially guaranteed a good job. And we have a very good biophysics group in the physics department here. Keith Lidke and Jim Thomas. As I say, not only are you guaranteed a job where you'll probably be paid more than you'd be paid making weapons of mass destruction at one of our insane national laboratories, but you'd also be doing some good, and you might even be doing a hell of a lot of good. Derivatives of the Laplace transform. Well, just as inasmuch as the Laplace transform is simply related to the Fourier transform, and the Fourier transform is easy to differentiate, so is the Laplace transform. You differentiate it n times, you just get minus t to the n. And so if you know one Laplace transform, you know the other. For example, if you differentiate the Laplace transform, or you differentiate 1 over s n times, you get 1 over s to the n plus 1, and that's the Laplace transform of t to the n, and so forth. And also something very important in the theory of differential equations, and this is especially important in optics and electronics, electrical engineering, is this relation of what happens if you take the Fourier transform of the derivative of something. Well, you do an integration by parts, and as long as e to the minus st f of t goes to 0 at infinity, which of course because of this conversion factor it usually does, the Laplace transform of the derivative is s times the Laplace transform of the function, capital F of t, minus the function evaluated at 0. And similarly, the integral, well, when you integrate, all you have to do is integrate e to the minus st, you just get 1 over minus t. Do it n times, you get 1 over minus t to the nth power. So, with Laplace transforms, as with Fourier transforms, they're very easy to integrate and differentiate. Of course, when you do that, you have to keep in mind that if the function on the right-hand side, might not converge, so you can't just assume that everything works. You have to use some common sense to make sure that both sides are convergent integrals or convergent derivatives. Now, as I said, Fourier transforms allow you to solve differential equations when the differential operator is just a bunch of derivatives and can be, all kinds of derivatives, just as long as it doesn't involve the independent variable x, or in this case s. And so if you have some polynomial derivatives times an unknown function equals a source function, the way to solve the answer is you write f and j as Laplace transforms. And so, bingo, you get that, bingo, you get that, and now you differentiate f, and that means that p of d by ds hits e to the minus st, it turns p into p of minus s, the right-hand side is j. This equation just tells you that p of minus t, f of t is j of t, so f is just this. So the solution, or a particular solution of the inhomogeneous differential equation is f of s is e to the minus st, j of t over p of minus t. So you're done. Now the hooker in this is you have to be able to know what the Fourier transform of the source function is. If you know that, then you don't really have to know what f is, because you're going to write your answer in terms of the Fourier transform, the Laplace transform, I'm sorry, not Fourier, the Laplace transform of the source function, and then divided by the polynomial in minus t, and that gives you the answer. And then your answer is the Laplace transform of that ratio. Now that's a particular solution. There are also homogeneous solutions. That is to say, the general solution of P of d by ds on f equals j is an inhomogeneous solution that we just found, plus any solution such that P maps, any solution that P maps to 0, because you can always add that in. And so we're looking then for a general solution of the homogeneous equation, homogeneous differential equation. Homogeneous just means nothing on the right-hand side. And so one way of writing that is to say it's a Laplace transform of something arbitrary times a delta function, and what delta function of minus p. And why does this work? Because if you hit this with p of d by ds, that pulls down p of minus t. P of minus t times delta of p of minus t, 0. So the integral of that with h is 0 unless h is some crazily singular function. Yes?
So isn't P a differential operator?
Is what?
P?
P is a differential operator.
Yeah, so what do you mean by P of minus t?
What is P of minus t?
Yeah.
Good question. I will turn on the lights and use the blackboard. I'm just going to use the right-hand side. Okay, so suppose P of, what are we talking about? D by ds. Suppose this is just d by ds. Then P of minus t is just minus t. Or P of minus t, P of d by ds is d2 ds squared, or d by ds squared, then P of minus t is just minus t squared. Do you want a candy? You've asked a couple of questions. Do you want one?
Okay.
All right, so let me turn the lights back off. By the way, you may notice that when I write on the board, you can actually read the chalk. That's because I'm using a Korean chalk called Full Touch, which is quite marvelous. The Koreans, by the way, are, of all the countries in the world, they're the most underestimated. Well, I don't know if they're most underestimated. Many countries are underestimated, but Korea is one of the underestimated countries. And one of the great tragedies of the last 100 years is the way the Korean Peninsula has been treated, first by the Japanese from 1905 until 1945, and then Stalin thought it would be really cool to get the Americans to fight the Chinese in Korea to make sure that the U.S. didn't didn't become friendly with the Chinese, because Stalin's view of the Chinese always was that they were radishes. They were red on the outside but white inside. And that the Chinese were closet capitalists. And of course China has become a leading capitalist country. Okay, sorry for all the politics, but I was really trying to be historical. Anyway, so basically we want a homogeneous solution of this, So what we do is we just pick our nodes and pick out an arbitrary, reasonably well-behaved function h of t. We multiply it by delta of p of minus t. We integrate, and we write our overall function this way. So this is really a suitably general function. I mean, I can't imagine why in physics we'd want anything more general than that. You might say then, how do we invert a Laplace transform? But once again, I've been moving through this chapter pretty fast. So if you guys have more questions, it's highly appropriate to ask me to stop. Okay. By the way, when would you like the midterm? Inasmuch as the people who aren't taking the class seriously have caused me to have to write and grade a midterm and omit the lecture, which means you get taught less. All of these things I detest. If I were running the place, I would just give everybody A's and screw all the exams. I'd even drop the homework. Well, no, I'd assign the homework and urge you to do it. I wouldn't bother to grade it. Anyway, why don't you think about it? Send me an email as to when you want the exam. Tentatively, I'd say we'll have it the week after fall break. And so the question is, tell me whether you want it Tuesday or Thursday after fall break. And you can and do tell your comrades that they're the reason we're doing this. 6 students who skipped class today. Actually 7, because there's also somebody auditing the class. So we're going to invert a Laplace transform. Now this is a little bit of unusual mathematics, but it's perfectly straightforward in terms of the Fourier transform. As I said, with the Fourier transform and Dirac's delta function, you can almost do anything. And so here, what we're going to do is we're going to generalize the Laplace transform to a complex variable. So instead of f of s, we have s plus iu. And so that's e to the minus s plus iu times t. And then we say, all right, we want to make sure that what we want to do is we want now to integrate over u. And in fact, we don't want to just integrate over u, we want to integrate over the whole real line of u. That means we want to make sure s is large enough so this integral over u will converge. So we just pick s to be sufficiently positive. And then we integrate over u. And then we just do this. We just now have this integral over u, and I've written this thing then as, in terms of a Laplace transform, I've used t prime as the Laplace transform variable, and so I have e to the iut, and then e to the minus s plus iut prime. Anyway, this is just straightforward, combining these things. And then you combine the 2 exponentials, and you just get this. And now you see this is Dirac's delta function comes to our rescue. It's a delta function that does the integral for us. We get the answer. So the answer is e to the minus st. The inverse Fourier transform is just this funny integral over u of the Fourier transform at high enough real s. And of course the Fourier transform, as you know, Laplace transform, the higher s is, the nicer the Laplace transform behaves. And so this is the answer. This is the inversion formula. This is called the Bromwich integral or the Fourier-Mellon transform. Okay, we're out of time, and I've gone very quickly through this material, so I think we should stop at this point. I don't want me to faint from weakness, or you to, oh, that's the homework? Okay, we have homework to give out, but why don't you give me the homework and turn that off whenever you want. Tell me what your names are.